Hello everyone. Today I will present our study of fully dynamic independent sets for map labeling. It is a joint work with Joy Boer and Martin Neulenberg from TU Wien. Manual label placement has a long history in cartography. The task is to assign labels for geometric features like points, lines, and areas. Its general principles and guidelines include legibility, and the labels should be overlap-free. A challenge is to get a large subset of pairwise independent labels. This problem was translated almost 30 years ago into the automated label placement problem in computational geometry. Given a set of labels, their bounding boxes build a set of axis-parallel rectangles. And the geometric intersection graph introduced by this rectangle set represents their overlaps. Thus, an independent set in this intersection graph corresponds to a set of pairwise overlap-free labels. To distinguish maximal and maximum independent sets, we use MIS for inclusion maximum independent set and max-RS for maximum in these slides. The maximum independent set problem is NP-hard even on unit square intersection graphs. It is studied also in different geometric intersection graphs. Back to the map labeling problem, we study fully dynamic label sets, which means allowing both insertion and deletion of labels. In a semi-automatic label placement tool, the cartographer interactively inserts or deletes labels, and the framework updates the labeling, responding to the user's modifications spontaneously. Another example is maps with labels appear and disappear over time. For example, this Instagram map is based on a stream of geotagged uniform size photos on the social media. Dynamic labeling can be modeled as dynamic independent set problem. The maximal independent set problems on dynamic graphs has attracted significant attention in the last 2 years. There are several works on independent sets problem in geometric intersection graphs. We want to point out recently, Huntinger and her group studied the dynamic maximum independent sets for intervals, hypercubes, and hyperrectangles. And we study dynamic rectangles of two types. One is rectangles of uniform height and width. So for example, this situation arises in maps with uniform photos as labels. And the second one is rectangles of uniform height and arbitrary width. So think about maps with labels in the same font size. And at each time step, either a new rectangle is inserted or one is removed. As a baseline algorithm, we use the graph-based approach introduced by Asadi and his group. This algorithm MIS graph maintains the intersection graph explicitly and makes greedily updates to maintain a maximal independent set. The update time is bounded by the maximum degree of the intersection graph, and this degree is a natural barrier for vertex update in a dynamic graph. We introduce this approach, MIS-ORS. It models the intersection graph implicitly using a dynamic geometric data structure. Thus, it breaks this natural barrier of maximum degree with a sublogarithmic update time. After these two maximal independent set approaches, we also studied dynamic approximation algorithms for maximum independent sets. Besides two grid-based approaches, we introduce one approach called line in our paper. So it uses stable line partitioning and maintains a 2 approximate maximum impedance set. And due to time constraints, I will talk about MESORS and this approximation approach line. Please refer to our paper for the other 2 algorithms. This algorithm MESORS maintains a maximal impedance set dynamically for a set of unit height and a unit width rectangles is equal to a set of unit squares by an affine transformation. So for the ease of explanation, I will use squares in the following illustrations. So we compute the initial solution M by using a linear greedy algorithm. And we maintain 2 fully dynamic orthogonal range search tree. One is TR for the centers of rectangles in the this rectangle set R, and one for rectangles in the current solution M. The currently best fully dynamic data structure for orthogonal range search is with the dynamic fractional cascading. And this yields amortized sublogarithmic update time and all of k plus sublogarithmic query time for reporting k points. And to delete a rectangle R, if it was in the solution set M, after deleting it, we may have to add other rectangles in the solution set to make it maximal. These new free rectangles must intersect with this deleted rectangle R, and use graph term, we observe that the neighbor rectangles of R have their centers in square R2, which is a center with set length 2 and concentric with R. And if one rectangle intersects a neighbor of R, say a rectangle in the second neighborhood of R, its center must be in the square R4. So for a valid candidate which can be added to M, it must be a neighbor of R with its center is in R2, and it has no intersects with other rectangles in the current solution. So as just mentioned, actually here involved are rectangles in the second neighborhood of R in the solution set M, and their centers are in the square R4. So by searching R4 in this range tree for solution set, we could get all the rectangles which may intersect a neighbor of R in the current solution set M. And after that, we could determine a rectilinear polygon P. It contains all the centers of rectangles which intersect R and not a neighbor of other rectangles in M. Then we query tree R with polygon P. Notice here, we need to partition this polygon P in rectangles, and then we could perform orthogonal range query with these rectangles. If we find a center in P, its corresponding rectangle can be added in M. And after refining this polygon P, we continue querying further free centers. This process is repeated until no free center exists. And by a simple packing argument, a unit rectangle can have at most 4 independent neighbors. So this process will be repeated at most 4 times. And overall, this deletion update is in sublogarithmic time. For insertion, it's quite similar. Insert a rectangle R, we have to detect whether R can be included in the solution set M. We could do that by querying the range R2 in this solution set tree Tm. If none of its neighbor is in the current solution M, then we could add this rectangle in the solution set. And recall that any unit rectangle can have at most 4 independent neighbors. Therefore, a maximal independent set immediately implies a 4 approximate maximum independent set. Then we will see a 2 approximation algorithm for dynamic maximum independent set. And this approach line applies for rectangles of unit height and arbitrary width. In its processing, we define a set of horizontal lines, h with unit distance, such that each rectangle is stepped by exactly 1 horizontal line. And for each line, we compute a maximum independent set of rectangles stepped on this line. This can be done with a linear greedy approach. And notice here, rectangles stepped on different odd lines are separated by some even lines, and they are independent to each other. And it's the same for even lines. Thus, we could obtain a 2 approximate maximum independent set by using the algorithm of Agawa and his group. So precisely, we constructed 2 independent sets M odd and M even as the union of maximum independent sets on odd lines and on even lines. And due to the pigeonhole principle, the larger one of these 2 sets is a 2 approximate maximum independent set. So to maintain this approximation ratio 2, we need to maintain a maximum independent set for each single horizontal line. If the rectangles are stepped by 1 horizontal line, their intersections can be represented in an interval graph. So as a subproblem, we considered how to maintain a maximum independent set in a dynamic interval graph. A maximum independent set of interval graph can be founded by a linear greedy approach, which sweeps the intervals from left to right, and in each step choose the interval with the leftmost right endpoint and discuss its overlapping intervals. So it's also called earliest deadline in scheduling literatures. And to apply this sweep line approach dynamically, we built a balanced binary tree Ti storing the intervals of I in left to right order based on their left endpoints. Additionally, each tree node in this binary tree stores a pointer to the interval with the leftmost right endpoint in its subtree. So if one interval is selected already by the sweep line approach, we want to use this binary tree to determine the next selected one. For example, if this sweep line approach already selects S2, then we search for its right endpoint, and the right subtrees in the branches of the search path contains all the intervals totally right to this interval S2. And compare the intervals stored in this right subtrees. For example, S6, it is the interval with the leftmost right endpoint in this region. And S4 is the one for the middle region. Then we compare this interval stored in the subtrees. We could choose the one with the leftmost right endpoint as the next selected one. So here it is S4. So find the next selected one is in logarithmic time. And if we want to insert a interval ik, we first need to determine if this new interval ik should be chosen in the greedy sweep line approach. If so, we update the solution by applying this sweep line approach from this new interval in the solution set until we choose an interval which was in the original solution. Thus, no further solution flippings happen after it. And in the deletion process, the flipping is from the preceding interval before this deleted interval. This approach is output sensitive to the changes in the solution. It is bounded by the size of the maximum independent set. And back to the rectangle approach line. With our dynamic interval graph approach, we could maintain a maximum independent set for each stepping line. Thus, we could maintain this two approximate maximum independent set for rectangle set with O of omega log n, where omega is the size of the solution change on the affected line. We implemented the following 5 algorithms, and for partitioning-based approaches, they produce a lot of white space in practice. So, for instance, in this algorithm line, it ignores the rectangles stepped by either all the even or all the odd stepping lines completely. So we implemented for this kinds of algorithms their greedy augmented variants by greedily add independent but initially discarded rectangles. So, and in our experiment, adding this greedy optimization drastically improved the solution quality in all cases. The implementation is in C++, and the experiments run on our server. For the algorithm ESA.1.1, we use the dynamic orthogonal range search data structure provided by the geometric library SEGA. We created 3 types of benchmark data. In the uniform model, we generate centers of rectangles uniformly at random, and in the Gaussian model, it is an overlay of 3 Gaussian distributions where 70% of the centers from the first distribution, 20% from the second, and 10% from the third one. We also created 6 real-world data sets by extracting point sets from OpenStreetMap dataset. They have different distributions and densities. So in our first set of experiments, we compared these algorithms, including their greedy variance in terms of update time and size of the computed independent sets. Here we show the scatter plots for large Gaussian benchmarks with 10,000 unit rectangles and 400 rounds of update. And in the scatter plots, we use different colors for different algorithms and use dots for the original variants and use crossing for their greedy variants. The algorithms in the top left corner performed well in both measures. Focus on our best heuristic algorithm line and the 2 maximal independent set solvers. So, see the plot on the left. Our ESA.1.1 is faster than the general approach MES graph for insertions, and on deletions, they are comparably fast. For the heuristic line, its greedy variant is nearly as fast as the original line approach, and it improved the solution quality a lot. Next, we compare the solutions of our algorithm with the optimum solution. So that means in each step, we compute exactly maximum independent sets for small instances with max HS. It's a max SAT solver. These plots show the Gaussian instances with 1,000 rectangles with 100 updates. So here, the y-axis is the ratio of the computed solution with the optimum solution. In our experiment, all the algorithms provide better solutions than their theoretical approximation guarantees. MIS algorithms reach consistently about 90% of the optimum. And this MIS graph approach performs faster deletion on small instances with small vertex degrees. The greedy line is competing well, reaches 80% of the optimum, and is about 1 order of magnitude faster than the MIS algorithms. In our last experiments, we explore in more details the scalability of the algorithm for large instances. Except for this approach MIS graph, the algorithms grow slowly in terms of their runtime. And again, this greedy line is about 1 order of magnitude faster than the MIS algorithms. In this study, we investigated independent set problems on a dynamic set of rectangles. We design and implement algorithms that demonstrate the trade-off between update time and the approximation factor, both from a theoretical perspective and in an experimental evaluation. In this talk, I presented one maximal independent set solver, MIS-OIS, based on orthogonal range searching. We also introduced our best heuristic approach line, which is based on stepping line partitioning. Here we designed one algorithm for dynamic interval graph, which is of independent interest. Please refer to our paper for our other results. And in the experiment part, we showed plots of Gaussian models. And from the algorithm behavior on different benchmarks, our main observations are quite similar. So if the solution quality is a priority, then the MIS-OIS algorithm is the method of choice. It provides the best solution and it's quite scalable. And the greedy variant of the algorithm line makes a well-balanced compromise between time and solution quality. Our benchmark generators and source code are available in this webpage. There are 2 open questions we want to propose. One is if there is dynamic independent set algorithms for unit height rectangles with approximation ratio better than 2. Another one is studying similar dynamic problems on non-uniform geometric objects, for example, for general rectangles. That covers the main points. Thanks for your attention.